What specific problem does the proposed method or algorithm aim to solve in the context of pareidolia and computer vision?
The proposed method aims to address the problem of detecting pareidolic faces in images, which current state-of-the-art computer vision face detection systems struggle to identify effectively. Specifically, the research introduces the Faces in Things dataset, consisting of 5,000 annotated pareidolic face images, to evaluate and improve the performance of neural networks in recognizing these non-standard face representations. The study demonstrates that existing models, such as those trained on the wider face dataset, exhibit poor detection rates for pareidolic faces, even when detection thresholds are relaxed. By fine-tuning these models on the new dataset, the research shows a significant improvement in pareidolic face detection, suggesting that the algorithm can bridge the performance gap between machine detection and human perception of pareidolia. Ultimately, the work seeks to enhance the understanding of how pareidolia manifests in both human and machine vision, providing insights into the mechanisms behind this phenomenon.
How does the proposed method or algorithm work? Illustrate step by step the process of creating the Faces in Things dataset and how it is utilized in the experiments.
The Faces in Things dataset is created by first sampling candidate pareidolic images from the LAION-5B dataset, which contains 85 billion image text pairs. The researchers use clip retrieval to filter images based on text queries related to pareidolia, such as pareidolia and Faces in Things. After downloading the images, they check for duplicates and downsample them to 512 by 512 pixels, while preserving the aspect ratio. The images are then manually annotated using the VGG image annotation tool to identify and remove any samples containing actual human or animal faces, resulting in a dataset that includes bounding boxes and basic facial attributes of pareidolic faces. In the experiments, this dataset is utilized to evaluate the performance of state-of-the-art face detection models, specifically by fine-tuning them on the Faces in Things dataset to improve their ability to detect pareidolic faces, ultimately demonstrating that fine-tuning significantly enhances detection performance compared to models trained solely on human faces.
Can you come up with a simple yet illustrative example of how the fine-tuning process for pareidolic face detection is conducted? Walk through the major steps with relevant details from the methodology described in the paper.
The fine-tuning process for pareidolic face detection involves several key steps as outlined in the paper. First, a pre-trained face detection model, specifically the retina face architecture, is selected, which has demonstrated strong performance on the wider face dataset. Next, the model is fine-tuned on the newly created Faces in Things dataset, which consists of annotated pareidolic images, by replacing 90% of the original wider face training data with images from this dataset. This approach allows the model to learn to detect pareidolic faces without suffering from catastrophic forgetting of its previous training. The fine-tuning is conducted for 10 epochs using the AtomW optimizer, with a learning rate of 10⁻⁻⁴ and a weight decay of 5 × 10⁻⁻⁴. Finally, the performance of the fine-tuned model is evaluated against the original model to assess improvements in detecting pareidolic faces, demonstrating that the fine-tuning significantly enhances the model's ability to recognize these unique patterns.
What are the theoretical or practical benefits of using the Faces in Things dataset and the associated fine-tuning method on machine learning models?
The Faces in Things dataset provides a controlled environment to study pareidolia in both human and machine visual perception, allowing researchers to explore how modern computer vision systems can be fine-tuned to detect pareidolic faces effectively. By fine-tuning state-of-the-art models like RetinaFace on this dataset, we observed a significant improvement in pareidolic face detection performance, closing the gap between machine and human capabilities. This dataset also enables the investigation of various training interventions, such as incorporating animal faces, which was found to enhance the model's ability to detect pareidolic faces by roughly doubling its performance. Additionally, The dataset facilitates the development of mathematical models that predict conditions under which pareidolia is most likely to occur, contributing to a deeper understanding of visual perception mechanisms. Overall, the Faces in Things dataset not only aids in improving machine learning models, but also enriches the study of visual attention and object recognition in complex environments.
How was the effectiveness of the proposed method validated or tested in the experiments? What metrics or benchmarks were used to evaluate its performance?
The effectiveness of the proposed method is validated through a series of experiments that measure the average precision, AP, of the MobileNet and ResNet 50 RetinaNet architectures on the Faces in Things dataset. The experiments compare the performance of existing pre-trained models against those fine-tuned specifically for pareidolic face detection. Control groups are established using models trained solely on the original wider face dataset to ensure that the transfer learning procedure does not interfere with the measurement of pareidolic detection performance. Additionally, the study explores various training interventions, such as adding animal faces and applying data augmentations to assess their impact on pareidolic face detection. The results indicate that fine-tuning on pareidolic images significantly improves detection performance, with metrics showing that the addition of animal faces can close the performance gap between human-trained models and those trained on pareidolia.
What specific results were achieved with the new method, and how do they compare with existing models? Can you provide details on the performance metrics obtained?
The new method introduced in the paper, which involves fine-tuning a state-of-the-art neural network, RetinaFace, on the Faces in Things dataset, significantly improved the detection of pareidolic faces. Specifically, the fine-tuned models demonstrated a marked increase in average precision, AP, for pareidolic face detection compared to pre-trained models that were not fine-tuned on pareidolic data. The results indicated that while existing models exhibited some pareidolia, they fell short of the performance achieved by the fine-tuned models, which effectively closed about half of the performance gap between human-trained models and those specifically trained for pareidolia. Additionally, the addition of animal faces to the training data was found to roughly double the algorithm's ability to detect pareidolic faces, further enhancing performance metrics. Overall, the fine-tuning approach yielded a simple yet strong baseline for pareidolic face detection, showcasing a significant advancement over previous models that lacked targeted training on pareidolic images.